In this video, I'll talk about some of the reactions that organometallics do with carboxylic acid and its derivatives. Primarily with its derivatives, it does have a lot of limitations for what it can do with carboxylic acid, and we'll talk about that. Um, Among the derivatives, the most common ones that we want to be looking at is really your acid halides, so like acid chloride, esters, and anhydride. I didn't really draw the anhydride in there, but typically the anhydride is kind of in between the ester and the acid halide in terms of reactivity. So most commonly, whatever reaction you see with these two guys, the anhydride will do the same thing. But these are the two most common ones that you're going to be looking at. The acid, however, even though in terms of the leaving group, the OH is kind of relatively similar to the OR or ester's leaving group, the problem with the acid is that you actually have a hydrogen there that's fairly acidic. So you got to be really careful with when you're using the organometallics because they can run in an acid-base reaction with it. And we'll talk about it. How does that work? Now, primarily when I'm looking at the acid chloride or acid halides with esters and even anhydrides, they more or less do similar reactions with organolithium and Grignards. So either one of those will do pretty much the same type of reactions with any one of those functional groups. And how does that really work? If I give you one example, suppose I have an acid chloride here, or acid halide. I'm going to go ahead and draw two carbons there. And I use CH3Li, and I could have used CH3 MgBr here, but I want to use at least two equivalents for any one of those. All right, and what it really does, obviously, in the first step, I will have CH3 minus coming in as your nucleophile, and it will do the attack on that carbon here, just like you would seeing that in case of aldehydes and ketones as well. However, there is one slight difference that you would see in here, and that's something I have discussed in the beginning of this chapter as well. So I got a carbon chlorine here, I got an O minus here, and then obviously I got this methyl group attached. Now, as soon as this is made, typically in case of an aldehydes and ketones, we would just go ahead and protonate this oxygen and kind of be done with it. That's because aldehyde and ketones don't really have an leaving group. But here in the carboxylic acid derivatives, especially with the acid halides, esters, and the acid anhydride that's supposed to be right in between here, they have a good leaving group. I didn't talk about the amides here because amides have a bad leaving group, so they don't really react with organometallics in here. So what I'm going to get here is I'll have this kind of falling back and knocking this chlorine out after making the tetrahedral intermediate. So my reaction or my product at this point would look something like this. So I reform this pi bond here where I have attached one of the carbons already and I have the chloride kind of gone here. And if I was using, let's say, an ester, I would have the OR minus kind of gone as opposed to here I have the Cl minus kind of gone because they're both still in a leaving group. Then the reason why I use two equivalents, but as soon as that ketone is made here, that ketone is still reactive enough where it can react with organolithium and the Grignard. So I can go ahead and do the second attack here, and then this opens up. Typically, it doesn't really make the chiral center because remember, you're going to be adding two of the same things on that particular carbonyl carbon, so it's not going to be chiral at the end of the day. But remember, you are going to be adding it twice, and now you see the reason why you're actually adding it twice, because you have a leaving group where on the first attack the leaving group leaves, and then you ended up making this as your intermediate here. And now in the second step here, I want to go ahead and just use dilute acid or just water since it's just making an alcohol, and I'll just go ahead and protonate this. So just an acid-base reaction at this point, and I'll just go ahead and have this H installed in there. So you will be making an alcohol at the end of the day. Oops. You will be making an alcohol at the end of the day here, but with organolithiums and the Grignards, when you're using acid chloride, ester, or even an anhydride, you would have two of the R groups to be the same. So that's how you can tell that, okay, I'm going in there twice because in the first attack, the leaving group leaves. And sometimes you would see this being written as, okay, I'm using two equivalents, and sometimes they would say, okay, I'm just going to be using excess. Just kind of tells you that you're not using just one equivalent, but just more than one equivalent. Um, I do want to say that in terms of the reactivity between the acid halide and the esters and anhydrides, acid halide is the most reactive out there. So there is one reactions that acid halides would do that the other guys would not do with the organocuprates. So if I have, suppose, the same type of reaction here, so suppose if I have R, so acid halide, and I use an organocuprate here. So I'm going to go ahead and use CH3, 2Cu, ally here in the first step. So again, what I'm really getting at the end of the day here is the CH3 minus, but remember this CH3 minus is not as strong as an nucleophile as you would get from an organolithium and Grignard. So as a result, it does kind of do the tack here. You get an O minus here at the end of the day, and I still have the Cl here for momentarily, and now I got this methyl group attached with a new bond. But then again, I have a leaving group, so I want to go ahead and get rid of that leaving group from that tetrahedral intermediate. So this is in a tetrahedral intermediate. So I want to go ahead and reform the pi bond here. When I reform the pi bond, this chloride leaves, and what I get is a ketone. And remember one of the methyls here. So I could have a different R group here, or the R minus here, depending on what organocuprate I'm using. And I have a leaving group, which is going to be the Cl minus. Now remember what I have said earlier, that the organocuprate does not react with an aldehydes and the ketones. And the only thing the organocuprate is really going to react with among all these carbonyls is really the acid halides, and that could be acid chloride or acid bromide. And sometimes they may react with the anhydrides, but it's kind of an in-between, and sometimes they do, sometimes they don't, so it's not really talked that much. But they would not react with esters, they would not react with the acids or anything like that. They would only do the reaction with the acid halide, and even when they do that reaction with the acid halide, they would stop it at a ketone. They would not do the addition twice because they're not reactive enough to react with the ketone. That's because remember, your acid halides are actually more reactive than the aldehydes and the ketones to begin with. So that's one reaction that you want to keep in mind. The second one that I want to kind of talk about is, what does acid do? So if I have, suppose, a carboxylic acid, what this possibly can do. And now this also does a slightly different reaction depending on what organometallics I'm using. So obviously they're not going to react with the organocuprate. It's just going to be either the organolithium or the Grignard. Now if I'm using a Grignard here, so suppose I'm using CH3 MgBr here in the first step. So the first step is really going to be the attack of, or doing the acid-base reaction here. So when I'm running an acid-base reaction here, I'm grabbing this proton, and creating a carboxylate here. And that's really the sad story about the Grignard. The Grignards are actually not strong enough where they can do the attack again on the carbonyl, just because you get a negative charge in here. And then you kind of get stuck in there. So you can't really do anything after that. And in the second step, when you do the workup within a dilute acid, it actually go ahead and make the acid back. So there's really nothing going on as far as the Grignards go with the carboxylic acid. So it's kind of useless to use Grignard. However, if I was doing the same reaction with the organolithium, so I'm just going to copy this here for a minute. So what I'm going to change here is, instead of Grignard, I have an organolithium. So remember, the nucleophile that you get from an organolithium is actually stronger. So I want to make sure I use at least two equivalent or excess. And I could have used excess for the Grignard as well, but it doesn't really do anything even if you use an excess or two equivalent. So the first step again is going to be the same because remember this is also in a very strong base, so it's going to go ahead and remove this hydrogen and make an carboxylate here. But then since you have the second equivalent here, that CH3 minus actually has a potential to kind of go ahead and attack this carbonyl carbon and break that pi bond. Now the Grignard was actually not able to do that, so that's something you want to kind of keep in mind. That's the difference thing that you would see in here versus in case of Grignard here. So you have CH3 here. So you make this the hydrate here. So with an oxygen with a negative charge, eventually you can go ahead and protonate those. So I'm using an acid and water. So in the first step, I'll go ahead and protonate both of those oxygens to where it makes an hydrate. But remember, hydrates are actually not that stable for the most part. So what I can have at this point is since I'm kind of working it up with an acid in here, I can protonate one of those oxygens. Doesn't really matter which one. I go ahead and protonate one of those oxygens, and when I go ahead and protonate one of these oxygens, I'll end up getting, let's see. Okay, let's see. I already had a hydrogen there. I'll use one of the lone pairs to protonate. So I get a plus there. So that's on a good leaving group now. So plus water is your side product here. And now I can go ahead and get rid of this water because that's in a good leaving group. Just got to reform that pi bond here to knock the water out. So it knocks out the water and I get R and a CH3 here. And now all of a sudden I'm about to make a ketone here. So that's protonated now. So I want to go ahead and use water to kind of go ahead and grab this proton here. And this restores the electron density back onto the oxygen there. So it'll have an alone pair. So the difference really you would see here, if I was using an acid within a Grignard, all it really does, it does the deprotonation, and then the Grignard is not strong enough, even if you have an excessive Grignard, it's not strong enough to do the attack on that carbonyl. So it kind of gets stuck in here, and then you eventually ended up making an acid back, or the starting material, if you go ahead and protonate it. However, if you're using a lithium, organolithium, so in case of organolithium, remember that's more reactive. It does the same reaction in the beginning, so I'm going to use one equivalent of that to deprotonate that carboxylic acid, and then the second equivalent of that R minus, or the CH3 minus in this case, is able to go ahead and do the attack and make the hydrate. So once you have the hydrate, it will eventually kind of go ahead and gets converted to a ketone with this mechanism because you still have an acid in there.